There is a particle that carries the exact same electric charge as the electron. It responds to the exact same forces. It obeys the exact same quantum rules, but it is over 3,400 times heavier. And it survives for less than a trillionth of a second before violently tearing itself apart into a spray of lighter debris. The tau lepton is the heaviest known charged lepton, the heaviest member of the electron's own family. It behaves like the electron in almost every measurable way, except for one devastating difference: its mass. And that mass changes everything. It makes the tau unstable, explosive, impossibly short-lived. But here's the real mystery. The standard model of particle physics, our best theory of how matter works at the smallest scales, allows this particle to exist. It just cannot explain why it exists at all. If you find this kind of deep exploration fascinating, a quick like or subscribe really helps the channel grow. It is a small thing for you, but it makes a real difference for me. Now, let's begin. Let's start with something you already know, even if you've never thought about it in these terms. Everything around you, every object you can touch, every surface you can feel, every material you've ever interacted with is built from atoms, and every atom has electrons. The electron is one of the most familiar particles in all of physics. It carries a negative electric charge. It orbits the nucleus of every atom. It's responsible for chemistry, for the bonds that hold molecules together, for the electrical signals firing in your brain right now as you listen to these words. The electron is small, stable, and absolutely everywhere. It has a mass of about 0.511 mega electron volts, which is a unit physicists use to measure the mass of subatomic particles. In more familiar terms, the electron is extraordinarily light, about 1,836 times lighter than a single proton. If you could somehow weigh an electron on a bathroom scale, the reading would be approximately 9.1 times 10 to the negative 31 kilograms. That's a decimal point followed by 30 zeros, and then a 9. Almost nothing. The electron is so light that for most of human history, no one even knew it existed. It wasn't until 1897 that J.J. Thomson demonstrated the existence of the electron using cathode ray tubes, showing that there were particles smaller than atoms carrying negative charge. And yet, this tiny speck of charge is one of the most important objects in the universe. Without electrons, atoms couldn't form chemical bonds. Without chemical bonds, there would be no molecules. Without molecules, there would be no water, no proteins, no DNA, no life. The electron is the workhorse of the material world. Every electrical device you've ever used, every computer chip, every battery, every light bulb, they all depend on the motion of electrons. The entire field of electronics, every smartphone, every laptop, every server that powers the internet, all of it runs on electrons flowing through circuits. The electron doesn't just participate in physics, it makes modern civilization possible. Now, here's what makes the electron truly special from a physics perspective. It's stable. Completely, perfectly, absolutely stable. An electron sitting alone in empty space will never decay. It will never break apart into smaller pieces. It will never transform into something else. It will sit there for eternity, unchanged, carrying the same charge and the same mass it had the moment it was created. Not a billion years, not a trillion years, eternity. As far as we know, the electron is immortal. This stability isn't accidental. It's a consequence of the laws of physics. The electron is the lightest particle that carries electric charge. Electric charge is conserved, meaning it can't appear or disappear. It can only move from one particle to another. So, for an electron to decay, it would need to transform into something lighter that also carries electric charge. But there's nothing lighter than the electron that carries electric charge. The neutrinos are lighter, but they're electrically neutral. The photon is massless, but also neutral. There's simply nothing for the electron to become. So it just sits there, forever, locked into existence by the conservation laws of the universe. Every electron in the universe today is identical to every electron that existed billions of years ago. They don't age, they don't wear out, they don't degrade. An electron in your body right now is indistinguishable from an electron that was produced in the first moments after the Big Bang, nearly 14 billion years ago. This permanence is why the electron works so well as a building block. You can construct atoms from electrons and trust that those atoms will hold together for billions of years, long enough for stars to form, planets to cool, oceans to fill, and life to evolve. The stability of the electron is one of the reasons the universe can have stable, complex structures at all. So far, this probably sounds straightforward. The electron is a small, stable, negatively charged particle that forms the outer shell of every atom. It's been around since the beginning of the universe and will be around until the end. Simple enough. But here's where things get genuinely strange, because the electron isn't alone. It has relatives, and those relatives raise questions that have haunted physics for nearly a century. In the early 20th century, physicists started studying cosmic rays, the high-energy particles that constantly rain down on Earth from outer space. These particles are produced by violent events in the cosmos, by exploding stars, by the enormous magnetic fields around neutron stars and black holes, by the shock waves that ripple through interstellar gas. When these high-energy particles hit molecules in Earth's upper atmosphere, they produce showers of secondary particles that cascade down through the atmosphere. By studying these showers, physicists discovered new particles that didn't exist in ordinary matter. In 1936, while studying cosmic ray tracks in a cloud chamber, a device that makes the paths of charged particles visible as trails of tiny droplets, a physicist named Carl Anderson and his colleague Seth Neddermeyer discovered something unexpected. They found a particle that looked almost exactly like an electron. It had the same electric charge, -1. It had the same spin, 1/2. It interacted with the electromagnetic force in the same way the electron does. By every measure they could apply, it was an electron. Except for one thing. It was 207 times heavier. This particle was the muon, and when it was first discovered, it baffled everyone. It seemed like a perfect copy of the electron, but at a completely different mass. The physicist Isaac Rabi, who would later win the Nobel Prize for his work on nuclear magnetic resonance, famously responded to the discovery by asking, "Who ordered that?" It was a joke, but it captured a genuine confusion that persists to this day. Why would nature create a heavier version of the electron? The electron worked perfectly fine on its own. It did everything that needed to be done. Atoms, molecules, chemistry, electricity, all of it ran on electrons. There was no obvious reason for a heavier copy to exist. The muon didn't build atoms. It didn't participate in chemistry. It couldn't, because it was unstable. After about 2.2 microseconds, A muon would decay into an electron and 2 neutrinos. 2.2 microseconds might sound like a very short time, and it is by human standards, but in the particle physics world, it's actually reasonably long. Long enough that muons created in the upper atmosphere by cosmic rays can reach the ground before decaying, thanks to Einstein's time dilation at the near light speeds they travel. You have muons passing through your body right now, about 10,000 of them per square meter per minute. Cosmic ray muons created high in the atmosphere that have traveled all the way down to the surface. But functionally, the muon is useless for building anything. It appears briefly, lives for a couple of microseconds, and decays. It seemed like a spare part, a duplicate component that the universe had no use for. Physicists were puzzled, but they moved on. They catalogued the muon, measured its properties, incorporated it into their theories, and continued exploring. Then, in the 1970s, something far stranger happened. Something that took the puzzle of the muon and amplified it dramatically. A team of physicists working at the Stanford Linear Accelerator Center, known as SLAC, began noticing anomalous events in their particle detector. SLAC is a laboratory in Menlo Park, California, that houses one of the longest linear particle accelerators ever built. At the time, physicists there were using a machine called SPEAR, which stands for Stanford Positron Electron Accelerating Ring. SPEAR collided electrons with their antimatter counterparts, positrons, at energies higher than anyone had achieved before in this type of experiment. The collisions produced bursts of new particles, which the researchers studied carefully to learn about the fundamental forces and building blocks of nature. In the data from these collisions, the team kept seeing events that didn't match any known particle. Specifically, they were seeing events where an electron appeared alongside a muon with significant missing energy that suggested invisible particles, probably neutrinos, had carried some of the collision energy away. This combination was bizarre. In known physics, there was no process that would produce an electron and a muon together in this way. The only explanation was that the collision was creating a new, unknown particle, a particle heavy enough to decay sometimes into an electron and sometimes into a muon, producing these mixed events. The leader of this experiment was a physicist named Martin Perl. Perl had been born in New York City in 1927, the son of Jewish immigrants from Poland. He had studied chemical engineering before switching to physics, earning his doctorate from Columbia University in the 1950s. By the 1970s, Perl had become one of the leading experimentalists at SLAC, and he had a specific obsession. He wanted to find new leptons. Leptons are the family of particles that includes the electron and the muon. They're particles that don't feel the strong nuclear force, the force that binds quarks together inside protons and neutrons. Instead, leptons interact only through the electromagnetic force and the weak nuclear force. Perl had a hunch that there might be more leptons out there, heavier ones waiting to be discovered at higher energies. The muon had already shown that the electron wasn't unique. Maybe there was a third charged lepton, even heavier, waiting to reveal itself, and the anomalous events at SPEAR were starting to prove him right. Between 1974 and 1977, Perl and his team at SLAC carefully accumulated evidence for this new particle. The work was painstaking. Each anomalous event had to be analysed individually. Alternative explanations had to be ruled out. Background noise had to be subtracted. The statistical significance of the signal had to be established beyond reasonable doubt. Physics doesn't accept a discovery until the evidence is overwhelming, typically until the probability that the result is a random fluctuation is less than 1 in 3.5 million. Perl's team had to demonstrate that the anomalous events couldn't be explained by any known process, and that they were consistent with the production and decay of a new particle. They called it the tau, from the Greek letter tau, which stands for triton, meaning third. It was the third charged lepton, after the electron and the muon. The name was appropriate. This was the third time nature had created the same particle, and each time it had made it heavier. It's worth understanding exactly what Perl's team saw, because the evidence for the tau was indirect and subtle. They never saw the tau directly. What they saw were the products of the tau's decay. When a high-energy electron collided with a high-energy positron in the sphere ring, the two particles would annihilate each other, converting all their combined energy into a burst of pure energy in the form of a virtual photon. This virtual photon could then transform into any pair of particles, a particle and its antiparticle, as long as there was enough energy to create their combined mass. At the energy's sphere was running around 3.5 to 7 giga electron volts of total collision energy, there was enough energy to create a tau and an anti-tau simultaneously. Once created, both the tau and the anti-tau would decay almost immediately. Each would produce its own spray of decay products. Sometimes the tau decayed into an electron plus neutrinos, and the anti-tau decayed into a muon plus neutrinos, or vice versa. This produced the signature that Perl was looking for: events with one electron and one muon appearing on opposite sides of the detector, with significant missing energy carried away by the invisible neutrinos. This signature was important because no known physics could produce it. You couldn't get an electron and a muon appearing together in the same event from any known process at those energies. The only explanation was that something new was being produced. Something heavy that could decay into either an electron or a muon, depending on which decay path it randomly chose. And that two of these somethings were being created simultaneously, each independently choosing its own decay channel. But Perl had to be extremely careful. There were many possible alternative explanations for these events. Background noise from other well-understood processes could mimic the signal. Detector malfunctions could produce false readings. Misidentified particles could create apparent electron-muon pairs that were actually something else entirely. A stray pion misidentified as a muon, for example, could turn an ordinary event into an anomalous one. Perl and his team spent years systematically eliminating these alternative explanations, one by one. They checked their detector calibration obsessively. They looked for correlations between the anomalous events and known backgrounds. They varied the collision energy and watched how the rate of anomalous events changed, comparing it to what they would expect if the events were truly from a new particle being produced at threshold. The breakthrough came when they realized that the anomalous event rate behaved exactly as it should. If a new heavy particle with a mass around 1,800 mega electron volts was being created, at collision energies below twice this mass, there wasn't enough energy to produce a tau anti-tau pair, and the anomalous events disappeared completely. Above this threshold, the events appeared and their rate increased in precisely the way predicted by quantum electrodynamics for the production of a new heavy charged lepton. This energy dependence was the key evidence. It turned what might have been a statistical fluctuation or an experimental artifact into a genuine discovery. The anomalous events didn't just exist, they turned on and off at exactly the collision energy you'd predict for a new particle with a specific mass. That's not something that background noise or detector errors do. The discovery was announced in a paper published in 1975, though it took several more years and additional experiments at other laboratories to fully confirm the result and nail down the properties of the new particle. The DESY laboratory in Hamburg, Germany, using their own electron-positron collider called DORIS, confirmed the tau's existence. The Cornell laboratory in Ithaca, New York, using the CESR collider, also confirmed it. By the late 1970s, there was no doubt. The tau was real. A third charged lepton with a mass of about 1,777 mega-electron volts had been discovered. The particle physics world had a new family member, and it was a deeply unsettling one. When they finally nailed down its mass, the result was staggering. The tau had a mass of 1,777 mega-electron volts. To be more precise, the current best measurement is 1,776.93 mega-electron volts, with an uncertainty of about 0.09 mega-electron volts. But for our purposes, 1,777 is close enough. Let me put that number in perspective because it's genuinely shocking. The electron has a mass of about 0.511 mega-electron volts. The muon has a mass of about 105.7 mega-electron volts. The tau has a mass of 1,777 mega-electron volts. That means the tau is approximately 3,477 times heavier than the electron, and about 16.8 times heavier than the muon. The mass jump from the electron to the muon is a factor of 207. The jump from the muon to the tau is another factor of almost 17. And the total jump from the electron to the tau is a factor of nearly 3,500. These numbers are not just large, they're disturbing. Because the mass is the only thing that changes. Everything else stays the same. The electric charge is the same, -1 fundamental unit. The spin is the same, 1/2. The quantum numbers that describe how the particle interacts with the electromagnetic and weak forces are the same. The mathematical equations that govern the tau's electromagnetic interactions are identical in form to the equations that govern the electrons. Swap the mass parameter and you can't tell the difference. The tau is the electron, wearing a different mass like a costume, and the costume is 3,500 times heavier. To appreciate how strange this is, consider an analogy. Imagine you discovered that somewhere in the world, there was an exact copy of your house. Same floor plan, same number of rooms, same windows, same doors, same roof, everything identical. Except that this copy was made entirely of lead instead of wood and brick. It weighed thousands of times more. It had the same shape, the same function, the same structure, but the material was inexplicably different. You want to know why. You want to know what process could create an exact copy of something while changing only one property by such a huge amount. You'd want to understand the mechanism behind this bizarre replication. That's the tau problem. Now let's add another jaw-dropping fact. The tau is heavier than the proton. The proton, which is the heavy particle sitting at the center of every hydrogen atom, the particle that makes up most of the visible mass in the universe, has a mass of about 938 mega electron volts. The tau at 1777 mega electron volts is almost twice that heavy. A lepton, a particle in the same family as the delicate, lightweight electron, is heavier than the proton. This is deeply counterintuitive. Leptons are supposed to be the light particles. The word lepton itself comes from the Greek word leptos, meaning thin or small. But the tau makes a mockery of that naming convention. It's a lepton that outweighs many hadrons, the composite particles made of quarks that are supposed to be the heavy ones. The proton gets its mass from a completely different mechanism than the tau. The quarks inside a proton contribute only about 1% of the proton's total mass. The rest, about 99%, comes from the kinetic and potential energy of the quarks and gluons interacting through the strong nuclear force. The proton's mass is dynamical. It emerges from the complex dance of quarks and gluons bound together by the strongest force in nature. The tau, on the other hand, gets all of its mass from its coupling to the Higgs field. Every single mega electron volt of the tau's 1777 mega electron volt mass comes from this coupling. There's no binding energy, no internal dynamics, no constituent particles. The tau is a single, indivisible, point-like particle whose entire mass is a gift from the Higgs field, a gift whose size has no known explanation. Martin Perl received the Nobel Prize in Physics in 1995 for his discovery of the tau lepton. The Nobel Committee recognized that the discovery wasn't just finding another particle to add to the catalogue. It was revealing something deep and unexplained about the structure of matter itself. The existence of the tau showed that nature repeats itself in ways we don't understand. It creates copies of fundamental particles, identical in every respect except mass, with no apparent reason for doing so. The tau was the third generation's most dramatic representative, and its discovery confirmed that the pattern of repeated generations was real, not an accident. Let me be very clear about something. The tau doesn't violate physics. It doesn't break any rules. It doesn't contradict any known law. Every measurement of the tau is consistent with the standard model of particle physics is the most successful scientific theory ever constructed, in terms of the precision with which its predictions match experimental observations. The standard model predicts the tau's interactions correctly. It describes its decay modes correctly. It accommodates the tau as a third-generation charged lepton, and everything works out mathematically. The equations are satisfied. The predictions match the observations. But the standard model doesn't explain why the tau exists. It describes the tau. It accommodates the tau. It uses the tau in its calculations. But it doesn't explain why the universe needs a particle that's 3,500 times heavier than the electron, but otherwise identical to it. The standard model treats the tau's mass as a free parameter, a number that has to be measured experimentally and plugged into the theory by hand. The theory doesn't predict what the tau's mass should be. It doesn't predict that a third generation of leptons should exist at all. It simply allows for them and, when told they exist, describes them correctly. This is one of the most important distinctions in modern physics. There's a difference between describing something and explaining something. I can describe the weather today without being able to explain why it's raining instead of sunny. I can describe the color of your eyes without being able to explain why evolution selected for that particular pigment in your particular ancestry. Description and explanation are different things. The standard model describes the tau beautifully, but it doesn't explain it. And that gap between description and explanation is where one of the deepest mysteries in all of physics lives. Now let's talk about what happens to the tau once it's created, because its fate is as remarkable as its existence. The tau lives for approximately 2.903 times 10 to the negative 13 seconds. Written out, that's 0.000000000002903 seconds. About 290 femtoseconds. A femtosecond is 1 quadrillionth of a second, 1 millionth of 1 billionth of a second. Let me try to give you a sense of how incomprehensibly brief this is. Light is the fastest thing in the universe. It travels at about 300,000 kilometers per second. In 1 second, light can circle the entire Earth 7.5 times. Light is unimaginably fast. And in the time it takes a tau to be born and then destroy itself, light travels only about 87 micrometers. 87 micrometers is roughly the width of a human hair. In the time it takes a photon to cross a single strand of hair, the tau has already lived its entire existence and ceased to be. Let's try another comparison. A nanosecond is 1 billionth of a second. Computer processors operate on nanosecond timescales. A single clock cycle of a modern computer takes about 1/3 of a nanosecond. In that tiny sliver of time, a tau could have been created and destroyed over 1,000 times over. The tau's lifetime is about 1,000 times shorter than a single clock cycle of the fastest computers ever built. Or think about it this way. If you could somehow slow time down so that 1 femtosecond lasted as long as 1 second, the tau would live for about 290 seconds, roughly 5 minutes. But in that same slowed down universe, a human heartbeat would take about 31 million years. Your heart wouldn't even begin to contract before entire geological ages had passed. That's how brief the tau's existence is compared to processes we can perceive. Now, compare the tau's lifetime to the lifetimes of its lepton relatives. The electron, as we discussed, lives forever. Infinite lifetime. It never decays. The muon lives for about 2.2 microseconds, which is 2.2 millionths of a second. That's short by everyday standards, but in particle physics, it's fairly long. Long enough that muons created in cosmic ray showers can travel several kilometers through the atmosphere before decaying. Long enough that physicists can create beams of muons in the laboratory and study them at leisure. The muon is a particle you can work with. The tau, on the other hand, lives for about 290 femtoseconds. That's about 7.5 million times shorter than the muon's lifetime. If the muon's lifetime was stretched to the length of an average human lifespan, about 80 years, then the tau's lifetime would correspond to about 5.5 minutes on the same scale. An entire human life reduced to the time it takes to boil an egg. The muon at least gets to live for a while, relatively speaking. The tau barely flickers into existence before it's gone. 3 particles in the same family. One lives forever. One lives for microseconds. One lives for femtoseconds. Same charge, same spin, same fundamental identity. Wildly, incomprehensibly different lifetimes. The factor between the electron's infinite lifetime and the tau's femtosecond lifetime is, well, infinite. And the factor between the muon's microsecond lifetime and the tau's femtosecond lifetime is about 7.5 million. These aren't small differences. They're differences so large that the three particles might as well exist in different universes, even though they're supposed to be the same kind of thing. Why does the tau decay so quickly? The answer lies in its enormous mass and the nature of the weak nuclear force. The weak force is one of the four fundamental forces of nature, alongside gravity, electromagnetism, and the strong nuclear force. The weak force is the fundamental force responsible for certain types of radioactive decay. It's the force that allows one type of particle to transform into another type. When a neutron decays into a proton inside an unstable atomic nucleus, the weak force is what drives that transformation. When the sun converts hydrogen into helium through nuclear fusion, the weak force is involved at a crucial step. The weak force is responsible for many of the most important processes in the universe. The weak force operates through the exchange of very massive particles called W and Z bosons. The W boson, which comes in positive and negative versions called W plus and W minus, has a mass of about 80.4 giga electron volts, or about 80,400 mega electron volts. The Z boson is even heavier, at about 91.2 giga electron volts. These masses are enormous by particle physics standards, roughly as heavy as an atom of rubidium or zirconium. Because the W and Z bosons are so heavy, the weak force is extremely short-ranged. It only operates over distances of about 10 to the negative 18 meters, which is about 1,000th the diameter of a proton. At any distance larger than this, the weak force is effectively zero. This extreme short range is why the weak force is called weak. The fundamental coupling strength of the weak force isn't actually that different from the electromagnetic force. But because its carrier particles are so massive, the force only operates at incredibly tiny distances, which makes it appear weak in most situations. If the W and Z bosons were massless like the photon, the weak force would be comparable in strength to electromagnetism. It's the mass of its carriers that suppresses it. Now, here's the key principle that determines the tau's fate. When a particle decays through the weak force, the rate of that decay depends very strongly on how much energy is available for the decay products. This is because the decaying particle doesn't actually produce a real W boson, which would require more energy than the tau possesses. Instead, it produces what's called a virtual W boson, a quantum mechanical fluctuation that temporarily violates the conservation of energy for a very brief period, allowed by the Heisenberg uncertainty principle. The heavier the decaying particle, the more energy it can pour into this virtual fluctuation, and the more readily the decay proceeds. For charged leptons decaying through the weak force, the decay rate follows a dramatic power law. The rate is proportional to the fifth power of the particle's mass. The fifth power. This is an extremely steep relationship. If you double the mass, the decay rate increases by a factor of 2 to the fifth, which is 32. If you triple the mass, the decay rate increases by 3 to the fifth, which is 243. And if you increase the mass by a factor of 16.8, which is the ratio of the tau mass to the muon mass, the decay rate increases by 16.8 to the fifth power, which is approximately 1,340,000. That's why the tau decays roughly 1,000,000 times faster than the muon. The enormous mass of the tau gives the weak force so much more energy to work with that the decay proceeds at a furiously rapid pace. This fifth power relationship is called the Sargent rule in nuclear physics, where it was first derived for nuclear beta decay. It arises from the quantum mechanical calculation of the decay probability, which involves integrating over all the possible ways the decay products can share the available energy and momentum. The more energy available, the more ways there are to distribute it. And the integral grows as the fifth power of the energy. This is a universal result in quantum mechanics. It applies to any decay mediated by the weak force where the mass of the decaying particle is much less than the mass of the W boson. Let me try to make this more intuitive with an analogy. Imagine a ball sitting on top of a hill. The ball represents the unstable particle, and the valley below represents the lower energy state it wants to decay into. The height of the hill represents the available energy. A ball sitting on a small bump has a limited number of ways to roll down. It can go left or right, but that's about it. Now imagine the ball is sitting on top of a massive mountain with dozens of valleys, ridges, and paths leading downward. There are far more ways for the ball to reach the bottom. It has more options, more routes, more possibilities. The tau is like the ball on the mountain. Its enormous mass gives it so much available energy that there are vastly more ways for it to decay compared to the lighter muon, which is sitting on a much smaller hill. More available energy means more decay paths, which means faster decay. The fifth power dependence makes this effect extraordinarily dramatic. A small increase in mass produces a huge increase in decay rate. This is why the tau, despite being only about 17 times heavier than the muon, decays about 1,000,000 times faster. The relationship between mass and decay rate isn't gentle, it's explosive. There's another way to think about why mass matters so much for weak decay rates. The weak force operates through the exchange of W bosons, which have a mass of about 80,000 mega-electron volts. Because the W boson is so much heavier than the tau can't produce a real W boson when it decays. There isn't enough energy. Instead, the decay proceeds through a virtual W boson, a quantum mechanical fluctuation that borrows energy from the vacuum for an incredibly brief instant. The Heisenberg uncertainty principle allows this borrowing, but only for a time inversely proportional to the amount of energy borrowed. The tau, being heavy, needs to borrow less energy relative to its total mass than the muon does. The virtual W boson that mediates the tau's decay is closer to being real than the virtual W boson that mediates the muon's decay. And a more nearly real intermediate particle means a faster process. This isn't a precise description of the mathematics, but it captures the physical intuition. The tau's mass doesn't just give it more energy to distribute among decay products, it also makes the quantum mechanical tunneling process that underlies weak decay more efficient. But there's something even more remarkable about the tau's decay, something that makes it genuinely unique among leptons. The tau is so heavy that it can decay in ways that the electron and muon cannot. The electron can't decay at all because there's nothing lighter for it to become while conserving electric charge. The muon can only decay into an electron and 2 neutrinos. That's it. The muon isn't heavy enough to produce anything else. The products of the muon's decay, an electron, a muon neutrino, and an electron antineutrino, are all much lighter than the muon, and there's no other combination of particles that the muon has enough mass to create while still conserving charge, Lepton number, and other quantum numbers. The tau, however, is heavy enough to produce hadrons. Hadrons are composite particles made of quarks, like pions and kaons. These are particles that feel the strong nuclear force. They're the same kinds of particles found inside atomic nuclei. No other lepton can do this. The electron and muon are too light to create hadrons when they decay, but the tau, with its mass of 1,777 mega electron volts, has more than enough energy to produce various combinations of pions, kaons, and other mesons. This gives the tau an unusually rich set of decay channels. Let me walk through the major ones. About 17.82% of the time, a tau decays into an electron, a tau neutrino, and an electron antineutrino. This is called the electronic decay channel. About 17.39% of the time, a tau decays into a muon, a tau neutrino, and a muon antineutrino. This is the muonic decay channel. These two channels together account for about 35% of all tau decays, and they're called leptonic decays because all the visible products are leptons. The remaining roughly 65% of tau decays produce hadrons. About 11% of all tau decays produce a single charged pion plus a tau neutrino. Another roughly 26% produce a charged pion accompanied by one or more neutral pions. About 10% produce 3 charged pions plus a tau neutrino. There are channels involving kaons, channels involving multiple pions with various charges, channels involving the ETA meson, and many others. The total number of distinct hadronic decay modes of the tau is enormous. Physicists have measured dozens of separate channels, each with its own precisely determined branching ratio. This hadronic decay capability is what makes the tau unique among leptons. It's a lepton that produces hadrons, a particle that interacts only through the electromagnetic and weak forces, that has no color charge and therefore doesn't feel the strong force directly, yet it produces particles that are bound, states of quarks held together by the strong force. The tau bridges the gap between the leptonic world and the hadronic world. It's a lightweight particle in classification that behaves like a heavyweight in practice. This bridging role makes the tau enormously valuable for physics. By studying the different ways the tau decays and measuring the precise rates of each channel, physicists can test fundamental predictions of the Standard Model with extraordinary precision. Every decay channel is a prediction. The Standard Model tells you exactly what fraction of tau should decay into each possible set of final particles. If the measured fraction matches the predicted fraction, the theory passes the test. If it doesn't match, something new might be going on. The hadronic decay channels of the tau are especially useful because they provide a clean way to study the strong force at relatively low energies. In a regime where the strong force is extremely difficult to calculate from first principles, the strong force gets stronger at lower energies, which makes perturbative calculations, the standard mathematical toolkit of particle physics, unreliable. But the tau's decays into hadrons provide experimental data that can be compared with theoretical predictions, testing our understanding of the strong force in this challenging regime. But detecting something that lives for 290 femtoseconds is extraordinarily challenging. You cannot watch a tau particle. You cannot track its motion across a detector. You cannot observe it interacting with other particles or bouncing off a target, or doing anything at all. By the time any detector could register its presence, the tau is already gone. It has already decayed into other particles. What physicists actually detect are the decay products, the electrons, muons, pions, kaons, and invisible neutrinos that the tau produces when it disintegrates. A tau produced in a particle collision typically travels less than a millimeter before decaying. often much less. In its own rest frame, the tau would travel about 87 micrometers, as we calculated from its lifetime and the speed of light. In a collider, the tau is moving fast, so time dilation stretches this to a few hundred micrometers or more, depending on its energy. Some taus travel a bit more, some a bit less, depending on their energy and the random nature of quantum mechanical decay. But the distance is always tiny, always sub-millimeter, always far too short to track with conventional particle detectors. So physicists have developed sophisticated techniques for identifying tau decays from the debris they leave behind. They look for specific signatures. A tau decaying leptonically looks like a single electron or muon, emerging from the collision point with significant missing energy. The energy carried away by the neutrinos that escape the detector. A tau decaying hadronically looks like a narrow cone or jet of 1 or 3 charged particles, sometimes accompanied by photons from neutral pion decays, also with missing energy. These signatures are distinctive enough that physicists can identify tau decays with reasonable confidence, even though the tau itself was never directly observed. Modern particle detectors are marvels of engineering, built with layer upon layer of different detecting materials. The innermost layers, closest to the collision point, are made of silicon sensors that can track charged particles with micrometer precision. These are followed by tracking chambers filled with gas that record the paths of charged particles as they ionize the gas molecules. Outside the tracking systems are electromagnetic calorimeters, dense blocks of material that absorb electrons and photons, measuring their energy. Beyond those are hadronic calorimeters, even denser materials that absorb hadrons. And at the very outside are muon detectors, because muons are the only charged particles that can penetrate all the inner layers without being absorbed. For tau decays, the silicon vertex detectors in the innermost layers are crucial. These detectors can sometimes resolve the tiny distance between the collision point where the tau was created and the point where the tau decayed. If the tau traveled far enough, say a fraction of a millimeter, the vertex detector can see that the decay products don't point exactly back to the collision point. They point to a slightly displaced vertex, a secondary decay point that's offset from the primary collision. This displaced vertex is a signature of a particle that lived just long enough to travel a tiny distance before decaying. It's one of the ways physicists confirm that they're seeing tau decays rather than prompt particle production. The technology required to see these displaced vertices is remarkable. The silicon pixel detectors used in experiments like ATLAS and CMS at the Large Hadron Collider have pixels as small as 50 by 50 micrometers. That's about half the width of a human hair. These tiny sensors are arranged in layers around the collision point, each layer recording the precise position where a charged particle passed through. By connecting the dots from layer to layer, physicists reconstruct the trajectory of each charged particle with micrometer level accuracy. This allows them to trace the particles back to their point of origin and determine whether they came from the primary collision or from a secondary decay point. Building these detectors is an enormous engineering challenge. The silicon sensors must operate in an incredibly harsh environment. They're just centimeters from the collision point, where millions of particle collisions happen every second. Radiation damage degrades the silicon over time. The electronics must be fast enough to keep up with the collision rate, and the entire apparatus must be precisely aligned, with each sensor knowing its position to within a few micrometers. These detectors represent some of the most sophisticated technology ever created by humans, all in service of detecting particles that live for less than a trillionth of a second. At the LHC, tau identification is particularly challenging because proton-proton collisions produce enormous numbers of particles. A typical collision at the LHC produces dozens or hundreds of particles, creating a spray of tracks in the detector. Somewhere in that spray, a tau might have been produced and decayed. Finding the tau's decay products among all the other particles is like finding a specific whispered conversation in a crowded stadium. Physicists use sophisticated algorithms, many now powered by machine learning and artificial intelligence, to sift through the data and identify the distinctive signatures of tau decays. These algorithms look for narrow jets of 1 or 3 charged particles, check for displaced vertices, calculate missing energy, and apply dozens of other criteria to separate genuine tau decays from the overwhelming background of other processes. Despite these challenges, the LHC experiments identified tau decays with impressive efficiency. In 2012, when the Higgs boson was discovered at the LHC, one of the key follow-up measurements was confirming that the Higgs boson decays into tau-anti-tau pairs. This measurement required identifying tau decays in the chaotic environment of proton-proton collisions and was one of the first direct confirmations that the Higgs field couples to leptons. The observation of the Higgs to tau-tau decay was announced in 2014, providing a direct measurement of the tau's Yukawa coupling to the Higgs field. The measured coupling was consistent with the standard model prediction, but the precision was limited. Future runs of the LHC and future colliders will improve this measurement dramatically. There's one more member of the tau's family that deserves attention. Every charged lepton comes paired with its own neutrino. The electron has the electron neutrino, the muon has the muon neutrino, and the tau has the tau neutrino. Each of these neutrinos is distinct. An electron neutrino produced in a nuclear reaction in the Sun is a different particle from a muon neutrino produced in a pion decay, which is different from a tau neutrino produced in a tau decay. They have different lepton flavor numbers, which the standard model treats as conserved in most interactions. The tau neutrino is perhaps the most elusive particle in the entire standard model. While the tau itself was discovered in the mid-1970s, and its associated neutrino was predicted to exist immediately as a logical consequence of the theory, the tau neutrino wasn't directly observed until the year 2000, 25 years after the tau's discovery. That's how hard this particle is to detect. The experiment that finally caught the tau neutrino was called DONUT, an acronym for direct observation of the NU tau. It was conducted at Fermilab, the particle physics laboratory about 40 miles west of Chicago. The DONUT experiment used a beam of high-energy particles to produce tau neutrinos through a clever chain of reactions. Protons from Fermilab's accelerator were slammed into a target, producing particles called DS mesons. These mesons decayed into tau particles, which in turn decayed into tau neutrinos. The resulting neutrino beam was aimed at a detector made of iron plates interleaved with sheets of photographic emulsion. Emulsion is a material that records the tracks of charged particles as they pass through it, much like photographic film captures light. Each charged particle passing through the emulsion leaves a trail of exposed silver halide grains. When the emulsion is developed, these trails become visible under a microscope. The resolution is extraordinary, down to a fraction of a micrometer, which makes emulsion one of the best ways to observe extremely short particle tracks. When a tau neutrino interacted with a nucleus in one of the iron plates through the weak force, it could produce a tau particle. That tau would then travel a tiny distance, typically less than a millimeter, before decaying into lighter particles. The emulsion sheets, sandwiched between the iron plates, recorded the tracks of both the tau and its decay products. The key signature was a kink in the particle track, a track that suddenly changed direction at the point where the tau decayed. Before the kink, the track was the tau. After the kink, it was the decay product. The abrupt change in direction was the smoking gun. The donut experiment detected 4 tau neutrino interactions. Just 4 events out of millions of neutrino interactions that occurred in the detector. But those 4 events, each showing the characteristic kink of a TAU being produced and then decaying, were enough to confirm that the tau neutrino exists as a distinct particle. It was the last standard model fermion to be directly observed, the final piece of a puzzle that had been assembled over the course of a century. And this brings us to the heart of the mystery, because the puzzle isn't just the tau, it's the pattern of 3 generations. The first generation of matter consists of 4 particles: the electron neutrino, the up quark, and the down quark. These 4 particles are all you need to build everything you see. Protons are made of 2 up quarks and 1 down quark. Neutrons are made of 1 up quark and 2 down quarks. Electrons orbit the nucleus, held in place by electromagnetic attraction. Electron neutrinos are produced in the nuclear reactions that power the sun. Every atom in every object, every molecule in your body, every star in the sky, every planet, every grain of sand, every drop of water, all of it is made from these 4 particles, and nothing else. The first generation is sufficient. It's complete. It handles everything the visible universe needs. The second generation consists of the muon neutrino, the charm quark, and the strange quark. These particles are heavier copies of the first generation. The muon is 207 times heavier than the electron, but otherwise identical. The charm quark is much heavier than the up quark, but plays the same role in the theory, sitting in the same position in the mathematical structure. The strange quark is heavier than the down quark, occupying the analogous slot. These second generation particles don't build stable matter. They're produced in high energy collisions and cosmic ray showers. They exist briefly, and they decay back into first generation particles. They seem unnecessary from a structural standpoint. And the third generation consists of the tau neutrino, the top quark, and the bottom quark. The tau is 3,477 times heavier than the electron. The top quark is the heaviest fundamental particle ever discovered, with a mass of about 173 gigaelectron volts, or 173,000 megaelectron volts. That's roughly the mass of an entire atom of gold, packed into a single, point-like particle with no internal structure. The bottom quark has a mass of about 4.2 gigaelectron volts, much heavier than the down quark's roughly 5 megaelectron volts. These third generation particles are even more unstable than the second generation. They decay even faster. They're even further from the stable matter that makes up the world you experience. And yet they exist. They're real. They've been created and measured in laboratories. Nature made them. And the question of why has no answer. This 3-generation structure is one of the most striking and most unexplained features of the natural world. The standard model accommodates 3 generations perfectly. Its mathematics works with any number of generations. You could write down a standard model with 1 generation, 2 generations, 4 generations, or 17 generations, and the math would still be self-consistent. The theory doesn't predict 3. It just allows it. The number 3 is an input, not an output. It's something physicists have to measure and then put into the theory by hand. Why 3? Why not 2? Why not 4? Why not 1? If the first generation is sufficient for building all stable matter, why does nature bother creating heavier, unstable copies? Why create a heavier electron that can't build atoms and decays in femtoseconds? Why create a heavier up quark that weighs as much as a gold atom and decays before it can even form a hadron? These are not rhetorical questions. They are among the deepest open questions in fundamental physics. And the tau, as the heaviest charged lepton, the particle that sits at the extreme end of this generational pattern, is perhaps the most dramatic illustration of the problem. The mass pattern makes things even more baffling. If the 3 generations had masses that followed some neat, simple progression, you might imagine a straightforward mathematical rule at work. If the muon were exactly 10 times heavier than the electron, and the tau were exactly 10 times heavier than the muon, you guess there was a factor of 10 between each generation. You'd look for an explanation of that factor. But the actual mass ratios are irregular and seemingly random. The electron to muon mass ratio is about 1 to 207. The muon to tau mass ratio is about 1 to 16.8. These are completely different ratios. There's no obvious pattern, no simple formula that generates these numbers. The same disorder appears in the quarks. The up quark has a mass of about 2.2 mega electron volts. The charm quark has a mass of about 1,275 mega electron volts. The top quark has a mass of about 173,000 mega electron volts. The ratio from up to charm is about 1 to 580. The ratio from charm to top is about 1 to 136. Completely different. No pattern. And the down-type quarks show yet another set of ratios with no discernible logic. The down quark has a mass of about 4.7 mega electron volts. The strange quark has a mass of about 95 mega electron volts. The bottom quark has a mass of about 4,180 mega electron volts. The ratio from down to strange is about 1 to 20. The ratio from strange to bottom is about 1 to 44. Again, no pattern. Each step up in generation multiplies the mass by a different factor. It's as though someone picked these numbers out of a hat. If you line up all 12 fermion masses, ignoring the neutrinos for the moment, you get a truly bewildering list. From lightest to heaviest, electron at 0.511 mega electron volts, up quark at about 2.2, down quark at about 4.7, strange quark at about 95, muon at about 106, charm quark at about 1,275, tau at 1,777, bottom quark at about 4,180, and top quark at about 173,000. These masses range from a fraction of a mega electron volt to hundreds of thousands of mega electron volts. The ratio between the lightest and heaviest is about 340,000 to 1. There's no known mathematical formula that generates this list. No equation into which you can plug a generation number and get the correct mass out. Physicists have tried. They've looked for patterns, searched for hidden ratios, tested mathematical relationships between the masses. Some interesting approximate relationships exist. For instance, the ratio of the muon mass to the electron mass, about 207, is somewhat close to certain combinations of fundamental constants. And the Koide formula, discovered by the physicist Yoshio Koide in 1981, relates the masses of the 3 charged leptons in an intriguing way. The formula states that the sum of the electron, muon, and tau masses divided by the square of the sum of the square roots of these masses equals 2/3. When you plug in the actual measured masses, this ratio comes out to approximately 0.666661, which is astonishingly close to the predicted 2/3. The Koide formula has no known theoretical justification. It might be a coincidence, it might be a clue, no one knows. It's been checked and rechecked over the decades as measurements of the lepton masses have become more precise, and it continues to hold. If it's not a coincidence, it suggests some deep mathematical relationship between the 3 charged lepton masses. A relationship that no current theory can explain. But attempts to extend the Koide formula to the quark sector have met with mixed results. It works approximately for some combinations of quarks, but not for others. Its status remains uncertain, a tantalizing hint that might lead somewhere profound or might lead nowhere at all. The neutrino masses add another layer of mystery. Neutrinos were originally thought to be massless in the Standard Model, but experiments in the late 1990s and early 2000s showed that neutrinos oscillate between flavors, a phenomenon where a neutrino of one type transforms into a neutrino of a different type as it travels. This oscillation is only possible if neutrinos have mass. The masses are incredibly tiny, at most about 1/10 of an electron volt, which is about 5 million times lighter than even the electron. But they're not zero. The neutrino masses don't follow the same pattern as the charged fermion masses. While the charged lepton masses increase dramatically from generation to generation, the neutrino mass differences are extremely small. We don't even know the absolute neutrino masses yet, only the differences between the squares of the masses. The pattern of neutrino masses might be very different from the pattern of charged lepton masses, which adds yet another wrinkle to the flavor puzzle. Why do the charged leptons have masses that span 4 orders of magnitude, while their neutrino partners have masses that are all clustered together near 0? The Standard Model, once again, has no answer. The mass hierarchy across all 12 fermions, 6 quarks, and 6 leptons spans an enormous range. If we exclude the neutrinos, whose masses are tiny and still being measured, the range goes from the electron at 0.511 mega electron volts to the top quark at about 173,000 mega electron volts. That's a range of almost 340,000. The lightest and heaviest fermions differ by a factor of hundreds of thousands. And the Standard Model has nothing to say about why these particular values were chosen by nature. Physicists call this the flavor puzzle. Flavor is the technical term for the property that distinguishes one generation from another. The electron, muon, and tau all have different flavor. The up, charm, and top quarks all have different flavor. And the biggest mystery about flavor is the mass spectrum. Why do the different flavors have the masses they have? What sets those values? The Higgs field gives particles their mass, yes. Each particle's mass depends on how strongly it couples to the Higgs field through a parameter called the Yukawa coupling. But the standard model doesn't predict the Yukawa couplings. Each coupling is a free parameter. The electron has a tiny Yukawa coupling. The tau has a Yukawa coupling that's about 3,500 times larger. The top quark has a Yukawa coupling of approximately 1, which is considered suspiciously close to unity, possibly a coincidence or possibly a clue. But the overall pattern of 12 Yukawa couplings, 12 seemingly random numbers that determine the masses of all the fermions, remains unexplained. There's a way to frame this that makes the problem feel especially sharp. The Higgs field explains the mechanism of mass generation. It's like explaining that a thermostat controls the temperature of a room. Fine. But who set the thermostat? Who dialed in the specific numbers? Why is the tau's Yukawa coupling set to the particular value that gives it a mass of 1,777 mega electron volts, rather than some other value? The mechanism is understood. The settings are not. In 1989, physicists at CERN used the Large Electron Positron Collider, known as LEP, to make one of the most important measurements in particle physics. They measured the width of the Z boson, which is one of the carriers of the weak nuclear force. The Z boson decays into pairs of particles, including pairs of neutrinos. Each type of neutrino that the Z can decay into makes the Z decay a little bit faster, which means the Z has a slightly shorter lifetime and a slightly broader width. By measuring the Z boson's width with extreme precision and comparing it to theoretical predictions for different numbers of neutrino species, physicists could count how many types of light neutrinos exist. The result was stunning in its clarity. The number of light neutrino species is 2.9840 plus or minus 0.0082, essentially 3. Not 2.5, not 3.5, 3, with a precision of about 0.25%. This measurement leaves almost no room for a fourth light neutrino. There are exactly 3 generations of matter with the light neutrinos, and nature stopped there. This makes the 3-generation structure feel even more deliberate, even more intentional, even more like it's trying to tell us something. 3 is not a random number. It's not some approximation of a larger number. It's a small, specific, finite integer. Nature created 3 copies of its fundamental building blocks, each one heavier than the last, and then stopped. No 4th generation, no 5th generation, 3 and done. This either a coincidence, which would be strange for such a specific number, or it's a consequence of some deeper principle that we haven't discovered yet. And if it's a deeper principle, we desperately want to know what it is. Some theorists have explored mathematical frameworks that might naturally produce 3 generations. In certain versions of grand unified theories, which attempt to merge the strong, weak, and electromagnetic forces into a single unified force at very high energies, the mathematics sometimes works out most naturally with 3 families fermions. In some string theory models, the number of generations is determined by the topology of the extra dimensions, the shape of the hidden spaces that string theory requires beyond the 3 dimensions of space and 1 of time that we experience. A particular topological property of these extra dimensions, called the Euler characteristic, can determine how many generations of particles exist. If the extra dimensions have a topology whose Euler characteristic gives 3, then 3 generations follow. Some Calabi-Yau manifolds, the mathematical spaces that string theory uses for extra dimensions, naturally produce 3 generations. But these ideas remain speculative. No version of grand unification or string theory has been confirmed experimentally. The true reason for 3 generations is still unknown. There's actually a beautiful argument from physics that hints that 3 generations might be necessary for the universe as we know it to exist. In 1973, the physicists Makoto Kobayashi and Toshihide Masukawa showed that if there are at least 3 generations of quarks, the standard model can naturally accommodate a particular type of asymmetry between matter and antimatter called CP violation. CP stands for charge conjugation and parity, and CP violation means that the laws of physics aren't perfectly symmetric between matter and antimatter. Some processes happen at slightly different rates for particles than for their anti-particle counterparts. With only 2 generations, the mathematics of the standard model doesn't allow for CP violation in the quark sector. The mixing matrix that describes how quarks transform between generations has too few parameters. But with 3 generations, there's exactly one complex phase in the quark mixing matrix that cannot be removed by redefining the quark fields. This one phase is what produces CP violation in the standard model. And CP violation matters enormously because it might be related to why the universe is made of matter rather than antimatter. In the first instance after the Big Bang, matter and antimatter were created in nearly equal amounts. If the laws of physics treated matter and antimatter with perfect symmetry, every particle would eventually have met its antiparticle and annihilated, leaving a universe of pure radiation with no matter at all. No stars, no planets, no life. But somehow, a tiny excess of matter survived. For every billion antiparticles, there were approximately 1,000,000,001 particles. That tiny excess is everything you see. All the galaxies, all the stars, all of us. The CP violation observed in the standard model, while real, is far too small to explain the observed matter-antimatter asymmetry. So there must be additional sources of CP violation beyond what the standard model provides. But the fact that 3 generations are the minimum needed for any CP violation at all is suggestive. It hints that 3 generations might not be arbitrary. They might be necessary for the universe to contain matter at all. Kobayashi and Masukawa received the Nobel Prize in Physics in 2008 for their theoretical prediction of CP violation with 3 generations. A prediction that was confirmed experimentally by the Babar experiment at SLAC and the Bell experiment in Japan. So the Tau's generation, the third, might not be as superfluous as it initially appears. Its existence enables a mathematical structure that allows for CP violation, which in turn might be connected to why matter dominates over antimatter. The third generation might not just be an unexplained copy. It might be a necessary feature of a universe that contains things rather than nothing. This connection goes even deeper through a mechanism called leptogenesis. Since the quark sector alone can't account for the missing antimatter, physicists have proposed that the lepton sector might provide the additional CP violation needed. If neutrinos violate CP symmetry, meaning that neutrino processes happen at slightly different rates than anti-neutrino processes, this could generate an asymmetry between leptons and antileptons in the early universe. What makes this idea powerful is that the early universe had mechanisms for converting a lepton asymmetry into a baryon asymmetry. Exotic quantum processes called sphalerons, which operate at extremely high temperatures above about 100 giga electron volts, can convert leptons into baryons while conserving the difference between baryon number and lepton number. These Phaleron processes were active in the first trillionth of a second after the Big Bang, when temperatures were high enough that the electroweak symmetry was still unbroken and the W and Z bosons were effectively massless. At these extreme temperatures, sphalerons acted like a cosmic mixing machine, redistributing any particle asymmetry between the lepton and baryon sectors. For leptogenesis to work, you need a mechanism that first creates a lepton asymmetry. The most popular version involves hypothetical, very heavy right-handed neutrinos, particles that would have masses far beyond anything current accelerators can probe. In the early universe, these heavy neutrinos would have been produced and then decayed. If CP violation occurs in these decays, meaning the heavy neutrinos decay slightly differently than their antiparticles, the result would be a small but crucial excess of leptons over antileptons. Sphalerons then convert part of this lepton excess into the baryon asymmetry that eventually became all the protons and neutrons in the universe, all the hydrogen that fuels stars, all the carbon and oxygen in your body, everything. The tau and its neutrino, as members of the heaviest lepton generation, play a specific role in the dynamics of leptogenesis. In some models, the lepton asymmetry is generated differently for each generation, and the tau generation's contribution can be particularly important because of the tau's large Yukawa coupling. The details depend on the specific model, but the general point is that all three lepton generations participate in the process, and the third generation, the tau's generation, can't be ignored. If leptogenesis is correct, then the particle that lives for less than a trillionth of a second, that seems to serve no practical purpose in the visible world, might have been an essential ingredient in the process that created all visible matter in the universe. Experiments are currently underway to test whether CP violation occurs in the neutrino sector. The Deep Underground Neutrino experiment, known as DUNE, is being constructed in the United States. It will send a beam of neutrinos 1,300 kilometers from Fermilab in Illinois to a massive detector deep underground in the former Homestake mine in South Dakota. By comparing how neutrinos and antineutrinos oscillate between flavors over this distance, DUNE hopes to determine whether CP violation occurs among neutrinos. If it does, it would be a major step toward understanding why the universe is made of matter. And the tau would be part of that story, as the heaviest member of the lepton family whose generation's neutrino participates in these oscillations. But even this doesn't fully solve the mystery, because the question isn't just why there are three generations. It's also why these particular three, why these particular masses, why this particular hierarchy. The Kobayashi-Maskawa mechanism requires 3 or more generations, but it doesn't specify the masses. It doesn't explain why the tau is 3,500 times heavier than the electron. It explains why 3 generations are needed for CP violation, but not why the 3 generations have the specific properties they do. The tau, with its extreme mass and its fleeting existence, sits at the intersection of all these mysteries. It embodies the generation problem more dramatically than any other particle. It's the most extreme copy, the heaviest replica, the particle that pushes the pattern of generational replication to its limit. And it does so while remaining perfectly consistent with every prediction of the standard model. Passing every test, obeying every rule, never once giving physicists the satisfaction of a clear violation that would point to something new. In recent years, there have been tantalizing hints that something might be slightly off. Measurements of certain decays of B mesons, particles containing bottom quarks, seem to show small differences in the rates at which these mesons decay into tau particles versus electrons or muons. If confirmed, such differences would violate lepton universality, the principle that all charged leptons interact identically except for their mass. The experiments at the LHCb detector at CERN and at the Bell and Bell 2 experiments in Japan have been looking for these violations with increasing precision. Lepton universality violation would be revolutionary. It would mean that some force beyond the standard model distinguishes between generations, treating the tau differently from the electron and muon. This could point toward new particles, new forces, new physics beyond anything we currently understand. For several years, the hints looked promising. The measurements showed deviations from standard model predictions at a level that was statistically suggestive but not yet conclusive. Physicists were excited but cautious, knowing the statistical fluctuations can mimic real signals. As more data has been collected, the picture has become less clear. Some deviations have weakened, others persist. The situation is still evolving. The experiments are still running. More data is being collected. The question of whether lepton universality is exact or slightly broken remains open. And the tau, as the heaviest lepton, is at the center of this search. Any violation of lepton universality is most likely to show up first in processes involving the tau, because the tau's large mass makes it most sensitive to the effects of hypothetical new heavy particles. The tau also plays a role in our understanding of the early universe. In the first fractions of a second after the Big Bang, when the temperature of the universe was above about 10 trillion degrees Kelvin, the energy density was so high that tau particles and anti-tau particles were being created and destroyed constantly in thermal equilibrium with the rest of the primordial plasma. At these temperatures, the mass of the tau was insignificant compared to the available energy. So taus were produced as readily as electrons. The universe was filled with a hot soup of all particle species, all interconverting freely. As the universe expanded and cooled, a critical transition occurred. When the temperature dropped below the threshold for tau-anti-tau pair production, roughly when the universe was about 10 picoseconds old, the taus and anti-taus annihilated each other, converting their mass energy back into radiation and lighter particles. After this annihilation era, no more taus existed as free particles. They had served their brief cosmological purpose and disappeared. Let me put that timeline in perspective. The universe is currently about 13.8 billion years old. That's about 4.35 times 10 to the 17 seconds. The era when taus were abundant, when the universe was hot enough to produce them freely, lasted less than a millionth of a second. The tau era was so brief that if you represented the entire history of the universe as a year, the tau era would occupy less than a millionth of a trillionth of a second of January 1st. It's as though the tau existed in the universe's very first breath, and then never again, except in the artificial conditions of our particle accelerators. And yet, During that incredibly brief epoch, the taus and anti-taus were enormously important. They were the part of the hot, dense plasma that filled the early universe, contributing to the total energy density that determined how fast the universe expanded. The annihilation of taus and anti-taus heated the remaining plasma, contributing to the radiation that would eventually become the cosmic microwave background. The tau's brief cosmological tenure wasn't unimportant. It was a crucial chapter in the first moments of existence, even if it ended almost before it began. But the tau neutrinos survived. They decoupled from the rest of the matter when the universe was about 1 second old, meaning they stopped interacting frequently enough to stay in thermal equilibrium with the surrounding plasma. Since then, these relic tau neutrinos have been streaming freely through the cosmos, gradually losing energy as the universe expands, cooling down from their initial high temperatures to their current frigid state. Today, the cosmic neutrino background contains about 112 tau neutrinos per cubic centimeter, along with similar numbers of electron neutrinos and muon neutrinos, for a total of about 336 neutrinos per cubic centimeter, filling all of space. Think about that for a moment. Right now, as you listen to these words, there are about 112 ancient tau neutrinos in every cubic centimeter of space around you. In every cubic centimeter. That's in the air you're breathing, in the walls of your room, in the ground beneath you, everywhere. These neutrinos were produced when the universe was 1 second old. They've been traveling through space for nearly 14 billion years, and they're passing through you right now, hundreds of trillions of them every second, completely undetectable by any technology we currently possess. The tau's legacy isn't just a line in a physics textbook. It's a cosmic relic that surrounds you at this very moment. We haven't been able to detect this cosmic neutrino background directly because the neutrinos are incredibly cold, with energies of roughly 1/10,000th of an electron volt, far too low for any current detector to sense. Detecting them is one of the great experimental challenges of the coming decades. Several proposed experiments, including Ptolemy at Princeton, are being designed to detect relic neutrinos by watching for the tiny energy they deposit when they interact with atoms of tritium, a radioactive isotope of hydrogen. If successful, this would be one of the most remarkable experimental achievements in the history of science, detecting particles that have been traveling since the universe was 1 second old. We can't detect this cosmic neutrino background directly, not yet, but we can detect its gravitational effects. The combined mass of all these relic neutrinos, spread across the observable universe, is significant enough to influence the expansion rate of the universe and the growth of cosmic structures like galaxy clusters and filaments. Measurements of the cosmic microwave background radiation, the afterglow of the Big Bang that permeates all of space, are sensitive to the number and masses of neutrino species. These measurements are beautifully consistent with exactly 3 species of light neutrinos, matching the 3 generations of the standard model. The tau's generation contributes its share of tau neutrinos to this cosmic bath, subtly shaping the large-scale structure of the entire visible universe. Let me try to bring all of this together because the tau's story is really the story of a question that sits at the foundation of modern physics and hasn't been answered. The standard model works. It works stunningly well. Its predictions have been confirmed by thousands of experiments over more than half a century, some matching observation to 10 or 12 decimal places. It describes all known fundamental particles and 3 of the 4 fundamental forces. The discovery of the Higgs boson in 2012 at the Large Hadron Collider was its crowning achievement, confirming the last major prediction of the theory. And yet the standard model is clearly incomplete. It has 19 free parameters that must be measured experimentally and inserted by hand. It doesn't include gravity. It doesn't explain dark matter or dark energy. It doesn't predict the masses of any fermion. It doesn't explain why there are 3 generations or why the generations have the mass hierarchy they have. The tau embodies this incompleteness more starkly than any other particle. It's perfectly described by the standard model. Every measurement matches. Every prediction works. But it's completely unexplained. Why is it there? Why is it that heavy? Why does nature need a 3rd generation charged lepton? The standard model can accommodate the tau, can describe its behavior, can predict its interactions with extraordinary precision, but it can't tell you why the tau exists rather than not existing. And that inability, that silence on the question of why, is perhaps the strongest argument that there must be a deeper theory beyond the standard model. A theory that derives what the standard model merely assumes. Physicists have spent decades looking for this deeper theory. They've proposed grand unified theories that merge the forces. They've proposed supersymmetry that relates fermions and bosons. They've proposed extra dimensions, string theories, technicolor models, preon models, and dozens of other frameworks. Some of these make specific predictions about the fermion mass hierarchy. Some predict relationships between quark and lepton masses. Some claim to derive the number of generations from geometric or topological properties of higher dimensional spaces. But none of them has been confirmed experimentally. The Large Hadron Collider, which collides protons at energies of up to 13.6 tera electron volts, the highest collision energy ever achieved, has found no evidence for supersymmetric particles, no evidence for extra dimensions, no evidence for any physics beyond the standard model. The desert beyond the standard model, as some physicists have started calling it, remains empty. No new particles, no new forces, just the standard model with its unexplained inputs and its 3 mysterious generations working perfectly. This is a frustrating situation. The standard model is too successful to abandon, but too incomplete to be final. The tau tells us that something is missing. Its inexplicable mass, its inexplicable existence as a 3rd generation particle. These scream that the standard model is not the whole story. And yet, every experiment designed to find what comes next has returned empty-handed. Some physicists believe the answer might come from studying the tau and the other fermions with even greater precision. The idea is that tiny deviations from a standard model predictions, deviations too small to detect with current experiments, but potentially observable with future technology, might reveal the fingerprints of new physics. This is the strategy of precision frontier physics. Instead of building bigger and more powerful colliders to produce new heavy particles directly, you make more precise measurements of known particles and look for tiny discrepancies that hint at the existence of something beyond the standard model. This approach has a long and distinguished history. Some of the most important discoveries in physics have come not from finding new particles directly, but from finding that known particles behaved slightly differently than expected. The anomalous magnetic moment of the electron, measured in the 1940s, deviated slightly from the prediction of the original Dirac equation. That tiny deviation led to the development of quantum electrodynamics, one of the most precise and successful theories in all of science. The tiny discrepancies in the orbit of Mercury, which Newton's theory couldn't quite explain, led Einstein to develop general relativity. Precision matters. Sometimes the most revolutionary physics hides in the 6th decimal place. The anomalous magnetic moment of the muon, measured with extraordinary precision at the muon G-2 experiment at Fermilab, is one current example of this approach. Every charged lepton has a magnetic moment, a measure of how strongly it interacts with magnetic fields. Quantum mechanics predicts this magnetic moment to many decimal places, including tiny corrections from virtual particles popping in and out of existence. The measured value of the muon's magnetic moment appears to differ from the standard model prediction by a small but potentially significant amount. If this discrepancy is real and not a result of experimental error or theoretical uncertainty in the standard model calculation, it would be direct evidence for new physics, new particles, or new forces that contribute to the muon's magnetic moment in ways the standard model doesn't account for. A similar measurement for the TAU would be incredibly valuable because the tau's larger mass makes it more sensitive to the effects of hypothetical heavy new particles. In general, the contribution of a new heavy particle to the magnetic moment of a lepton increases with the lepton's mass. So if there are new particles out there affecting the magnetic moments of leptons, their effect on the tau's magnetic moment would be larger than their effect on the muons, which in turn would be larger than their effect on the electrons. The tau would be the most sensitive probe, but measuring the tau's magnetic moment is extraordinarily difficult. The tau lives for only 290 femtoseconds. In the muon G-2 experiment, muons are stored in a magnetic ring for hundreds of microseconds, circling thousands of times while their spin precesses, allowing the magnetic moment to be measured with exquisite precision. You can't do this with the tau. The tau would decay long before completing even a fraction of one orbit. So physicists have to extract information about the tau's magnetic moment indirectly, from the properties of tau pair production in electron-positron collisions, or from the angular distributions of tau decay products. These indirect measurements are far less precise than the direct measurement possible for the muon, but they're improving. And with enough data, they might eventually reveal something unexpected. The Belle 2 experiment in Japan is one of the leading facilities for tau physics. It collides electrons and positrons at energies specifically chosen to produce large numbers of tau particles operating at the so-called B-factory energy, where B mesons and tau pairs are produced copiously. By collecting and analyzing billions of tau decays, measuring branching ratios and kinematic distributions and angular correlations to high precision, Belle 2 is testing the standard model in the Tau sector with unprecedented accuracy. The experiment began taking physics data in 2019 and is expected to continue for many years, accumulating an enormous dataset that will push the precision of tau measurements to new levels. The Large Hadron Collider at CERN also produces tau particles in abundance, though in a more challenging experimental environment. Proton-proton collisions at the LHC are messier than the clean electron-positron collisions at Belle 2, with many more particles produced in each event. But the sheer volume of data at the LHC compensates for this complexity. The ATLAS and CMS experiments, the two giant detectors at the LHC, have already made important measurements of tau properties, including measurements of the Higgs boson's decay into tau pairs. The Higgs boson decays into tau anti-tau pairs about 6.3% of the time, and measuring this rate precisely tests whether the tau's Yukawa coupling to the Higgs field is exactly what the standard model predicts. So far, the measurements are consistent with the prediction, but the precision is still limited, and future data could reveal a deviation. Future collider projects, still in the planning stages, could push tau physics even further. Several proposals are being discussed by the global physics community. A future circular collider at CERN, potentially 100 kilometers in How's circumference, could collide electrons and positrons at much higher luminosities than current machines, producing astronomical numbers of tau pairs. The International Linear Collider, proposed to be built in Japan, would provide clean electron-positron collisions at energies optimized for precision measurements. A muon collider, an even more ambitious concept that would collide beams of muons and antimuons, could reach even higher energies while maintaining the cleanliness of Lepton collisions. Any of these machines would be a factory for tau physics, producing tens of billions of tau pairs and allowing measurements of tau properties at a level of precision that today's experiments can barely dream of. If new physics exists, and if it couples differently to different generations of leptons, these future experiments would find it. The tau, as the heaviest lepton, would likely show the largest effects. The tau might be the particle that finally cracks the generation puzzle wide open, but we're not there yet. For now, the tau remains a perfectly measured enigma. A particle that fits perfectly into an incomplete theory. A fact in search of an explanation. Let me end with something that I think captures why the tau matters, not just to physicists, but to anyone who wonders about the nature of reality. The tau tells us that the universe has structure we don't understand. Not at the level of distant galaxies or abstract mathematics, but right here, at the most fundamental level of matter. The building blocks of everything, the particles that make up every atom of every object in the universe, have a pattern to them that we can observe but cannot explain. There are 3 copies of every fundamental fermion, each copy identical to the others except for mass, and no one knows why. This is not a minor detail. This is not a footnote in a physics textbook that only specialists care about. This is about the basic ingredients of reality. Why does the universe have the particles it has? Why do those particles have the properties they have? Why 3 generations rather than 1 or 17? These are questions about the deepest structure of the physical world. Questions that go to the heart of why reality has the form it does, and we don't have answers. Think about what we've accomplished in physics over the past few centuries. We've unified electricity and magnetism into a single theory. We've discovered that matter is made of atoms. We've split atoms and found protons, neutrons, and electrons inside. We've split protons and neutrons and found quarks. We've discovered the strong force, the weak force, the Higgs field. We've built accelerators that recreate conditions from a fraction of a second after the Big Bang. We've constructed the Standard Model, a theory so precise that some of its predictions have been confirmed to 10 or 12 decimal places. These are extraordinary achievements, among the greatest accomplishments of the human intellect. This is the heart of it. When we ask why there are 3 generations of matter, we have nothing. When we ask why the tau has a mass of 1,777 mega electron volts, rather than some other number, we have nothing. When we ask what determines the Yukawa couplings of the 12 fermions, what sets these 19 free parameters that define the particle content of the universe, we have nothing. Absolute silence. The deepest theory we have describes these parameters but cannot derive them. It accepts them as inputs without explaining where they come from. This situation is humbling. It reminds us that our understanding of nature, however impressive, remains incomplete. We can describe the universe with extraordinary precision. We can predict the outcomes of experiments to 10 decimal places. We can build technologies based on our understanding that work flawlessly. But we still don't know why the universe has the particular particles it has, with the particular masses they have, arranged in the particular pattern of 3 generations. There's a sense in which the Tau represents the cutting edge of human ignorance. Not ignorance in the pejorative sense, not a failure of effort or intelligence, but ignorance in the scientific sense, a precisely identified boundary between what we know and what we don't. The Tau's properties have been measured with great precision. We know exactly what the Tau does. We just don't know why it does it. We don't know why it's there. And that precisely delineated ignorance is incredibly valuable, because it tells us exactly where to look for the next breakthrough. Throughout the history of science, the most productive moments have been those when scientists could point to a specific, well-defined problem and say, "This is what we don't understand." Kepler could point to the precise mathematical shape of planetary orbits and say, "I don't know why they're ellipses." Newton answered him. Planck could point to the specific spectral distribution of blackbody radiation and say, "Classical physics can't explain this curve." His answer launched quantum mechanics. The Tau presents a similar situation. We can point to the specific mass of 1,777 mega-electron volts and the specific pattern of 3 generations and say, "We don't know why." The answer, when it comes, might launch a revolution in physics as profound as quantum mechanics or general relativity, or it might not. It's possible that the answers will come incrementally, through a series of small advances rather than a single dramatic breakthrough. It's possible that the flavor puzzle will be solved gradually, piece by piece, over many decades. It's even possible, though most physicists resist this idea, that the specific values of the Fermion masses are random, set by accident during the early universe, with no deeper explanation at all. In some versions of the multiverse hypothesis, the constants of nature vary from one universe to another, and we simply live in one where the values happen to allow complex structures and observers. In this view, asking why the Tau has the mass it has is like asking why you were born on a Tuesday rather than a Wednesday. There might be no deeper answer. It might just be chance. Most physicists find this unsatisfying. The 3-generation structure feels too specific, too precise, too structured to be random. The Coide formula works too well for 3 random numbers. The fact that exactly 3 generations are needed for CP violation feels too meaningful to be coincidence. The generation pattern looks like it's trying to tell us something, and physicists, by nature and by training, listen when nature speaks. The Tau is a particle that sits squarely in the middle of this mystery. It's the heaviest charged lepton, the most extreme copy, the particle that makes the generational puzzle impossible to ignore. You can look at the muon and think that maybe the universe just made one extra lepton by accident, a fluke, an echo, a minor variation on a theme. But once you see the Tau, with its mass of 1,777 mega-electron volts and its lifetime of 290 femtoseconds, you know this isn't an accident. This is a pattern. A deliberate, structured, threefold repetition of the same fundamental template at wildly different mass scales. And patterns in physics always have reasons. We just haven't found this one yet. And patterns demand explanations. Every great advance in physics has come from noticing a pattern in nature and asking why. Newton noticed that apples fall and the moon orbits and asked whether the same force could explain both. Maxwell noticed that electricity and magnetism were connected and unified them into electromagnetism. Einstein noticed that the speed of light was constant for all observers and derived special relativity. Patterns are clues. They're nature's way of hinting at deeper structure. The three-generation pattern of matter is one of the most obvious, most persistent, and most stubbornly unexplained patterns in all of physics. The tau stands at its apex. A particle that shouldn't need to exist, but does. A particle that the standard model describes perfectly, but explains not at all. Someday, perhaps, a deeper theory will make sense of all this. It will derive the masses of the electron, muon, and tau from first principles. It will predict the number of generations. It will explain why the Yukawa couplings have the specific values they have. When that theory is found, the tau's mass of 1,777 mega-electron volts will no longer be an arbitrary input. It will be a consequence, a result, something that follows inevitably from the deeper laws. And the three-generation pattern will go from being a mystery to being a theorem. That day hasn't come yet. The tau is patient. It's been appearing in high-energy collisions since the Big Bang, briefly flickering into existence and then vanishing over and over in every sufficiently energetic event anywhere in the universe. It appears in our particle accelerators, leaves its signature in our detectors, and challenges us to explain why it's there. There's something remarkable about the relationship between the tau and human knowledge. The tau was discovered less than 50 years ago. For all of human history before 1975, no one knew the tau existed. Ancient civilizations built monuments, developed mathematics, created art and literature, founded religions, waged wars, built empires, all without any awareness that the fundamental matter of the universe comes in three generations. The idea that the electron has a heavier cousin that outweighs a proton would have been incomprehensible to Newton, to Darwin, even to Einstein. The tau's existence is a product of a very specific era in human history, an era in which we learned to build particle accelerators powerful enough to recreate the conditions of the early universe and sensitive enough to detect particles that exist for less than a trillionth of a second. This puts the tau in a remarkable context. It's a particle that the universe has contained since the first microsecond after the Big Bang. Taus were being produced and annihilated in the primordial plasma 14 billion years ago. They existed before the first atoms formed, before the first stars ignited, before the first galaxies assembled, and yet no mind anywhere in the universe knew about them until a team of physicists in California noticed some anomalous events in their detector in 1974. For 14 billion years, the tau existed in the universe without being known. And now, in just the last 50 years, we've measured its mass, lifetime, decay modes, and interaction strengths to extraordinary precision. We've incorporated it into our most fundamental theory of nature. We've used it to test predictions and search for new physics. We went from complete ignorance to detailed knowledge in a geological eye blink. This is a testament to the power of the scientific method. We didn't need divine revelation to discover the Tao. We didn't need an ancient text to tell us about the 3-generation structure of matter. We figured it out ourselves through observation and experiment, through building machines and analyzing data, through the slow, painstaking accumulation of evidence, and the careful application of logic. The Tao is a discovery that belongs entirely to the human intellect. It's something we found because we looked, because we asked questions, because we refused to accept that our understanding of the universe was complete. And the questions the Tao raises are still open. That's perhaps the most important thing to take away from tonight's exploration. The Tao isn't a solved problem, it's a live mystery. The 3-generation pattern of matter is one of the biggest unsolved puzzles in fundamental physics. The mass hierarchy of the fermions is unexplained. The origin of the Yukawa couplings is unknown. The reason for exactly 3 generations is undetermined. These are active areas of research, with experiments running and theories being developed and tested right now, today, as you listen to these words. Somewhere in the world, at this very moment, a physicist is analyzing data from a tau decay at the Large Hadron Collider. Somewhere, a theorist is writing down equations that might explain the 3-generation structure. Somewhere, an engineer is designing a component for a future experiment that will measure the Tau's properties with even greater precision. The search for the answer to the Tau puzzle is ongoing. It hasn't stopped. It might take years, decades, or even centuries, but it will continue, because that's what science does. It doesn't accept mysteries, it interrogates them. They find things that don't make sense, and they refuse to accept them until they do. The orbit of Mercury didn't quite match Newtonian predictions, and that discrepancy led to general relativity. The spectrum of black-body radiation didn't match classical predictions, and that failure led to quantum mechanics. The Tau doesn't violate any prediction, but its unexplained existence, its unexplained mass, its unexplained role as the third in a family of 3, these point towards something beyond our current understanding. Every unexplained fact in physics is a door. The Tau is one of the most prominent doors that remains closed, and behind it might lie an entirely new understanding of why the universe has the particular structure it does. The electron builds atoms. The muon puzzles physicists. The Tau haunts them. 3 particles, same family, same charge, same spin. One lives forever. One lives for microseconds. One lives for femtoseconds. One weighs almost nothing. One weighs 200 times that. One weighs 3,500 times more. Same particle 3 times over, and no one alive today can say why. That's what the Tau really is. Not just a heavy electron, not just an unstable lepton, not just a line in the Standard Model's ledger. It's a signpost pointing toward unknown territory. It's a message from nature that says, "You're not done yet. There's something deeper here, something you haven't found. Keep looking." And physicists will keep looking, because that's what they do. They stare at the thing that doesn't fit until the universe blinks first. The Tau doesn't fit, not because it violates any law, but because no known law explains it. And that gap between what we observe and what we can explain is the most fertile ground in all of science. It's where discoveries live. It's where revolutions begin. The next time you think about the electron, the little particle that makes chemistry work, that carries current through wires, that holds atoms together, remember that it has a twin. An identical twin, except for mass. A twin that weighs as much as 2 protons, that lives for a fraction of a trillionth of a second, that decays into showers of pions and neutrinos, that exist for no reason anyone can explain. A twin whose very existence tells us that the deepest laws of nature remain hidden, waiting to be discovered. That twin is the Tau, and its existence is one of the most beautiful, frustrating, and important unsolved problems in all of physics. It's a reminder that science isn't finished, that the universe still holds secrets, that the most fundamental questions about why reality has the structure it does remain wide open, and that somewhere out there in the space of possible theories, there's an explanation waiting to be found. There's something profoundly hopeful about the Tau's mystery. It means the story isn't over. It means physics still has great chapters to write. It means that future generations of physicists will have the privilege of working on one of the deepest questions ever asked. Why does matter come in 3 generations? The answer to that question might change everything. It might connect particle physics to cosmology in ways we haven't imagined. It might reveal new forces, new symmetries, new principles that govern the behavior of matter at the most fundamental level. Or it might reveal something we can't even conceptualize yet. Something as surprising and transformative as quantum mechanics was to the physicists of the early 20th century. The Tau was born in the first breath of the universe and erased from it almost immediately. For 14 billion years after that, no Tau existed as a free particle anywhere in the observable universe. Not one. The cosmos had moved on without it. And then, in a laboratory in California, in the middle of the 1970s, human beings figured out how to recreate the conditions of the early universe, at least on a tiny scale. They accelerated particles to enormous energies, smashed them together, and created temperatures and densities that hadn't existed since the first moments after the Big Bang. And in those miniature recreations of the primordial fire, the Tau reappeared. After 14 billion years of absence, the Tau flickered back into existence, created by the same process that had produced it in the Big Bang, existing for the same fraction of a trillionth of a second, and decaying into the same spray of lighter particles. In a real sense, when physicists create Tau particles in their accelerators, they're bringing something back from the very beginning of time. They're recreating a piece of the early universe, a particle that was abundant when the cosmos was younger than a heartbeat and has been absent ever since. Every Tau produced at the Large Hadron Collider, or at Belle 2, is a tiny echo of the Big Bang. A momentary resurrection of something that the universe itself stopped producing 14 billion years ago. That's extraordinary. And the fact that we can do this, that we can reach back to the first moments of cosmic history and produce particles that haven't existed naturally for 14 billion years, and then study those particles with precision instruments and compare their behavior to our theoretical predictions, that's one of the most remarkable things humanity has ever accomplished. Thank you for joining me tonight on this journey into the heart of matter. If you found this exploration valuable, a like or subscribe would mean a lot. It helps me continue making these deep dives into the mysteries of the universe. Sleep well tonight, knowing that right now, in particle accelerators around the world, Tau particles are flickering in and out of existence, each one lasting less than a trillionth of a second, each one 3,500 times heavier than the electron, each one perfectly consistent with every law of physics we know, and each one completely, stubbornly, beautifully unexplained. Good night. And may you never think about particles the same way again.